These are the average values here. It's just the way it says here, original data, but the average of 5 readings for each of the error positions. And I used every other tick mark that's on the sheet that I have posted. Anyway, here we are, the leftmost marking is 40 millimeters away from the center, and it goes to the left. And this is 40 millimeters to the right. No, negative numbers here, positive numbers here. And so now we know if we get a negative number, we're off to the left. The center of the car is to the left of the path. And if it's positive, the center of the car is to the right of the path. So anyway, and you can see that the numbers, they kind of get larger on a sort of a diagonal as you move the thing across. And here is a plot of those numbers. And you can see now what I've talked about before. The center ones seem to have less gain for some reason than the outer ones, but no, it's okay, we'll fix that. And you can see also that, for instance, this leftmost sensor, it's when it's seeing only white, it's at a higher reading than all the other sensors actually when they see white. So we got to remove the zero offsets first, and then we got to correct the gain offsets. So that's the first thing that we're doing here, is I'm computing the minimum value of each of these columns. So the minimum value here is 813.6, and so and 629. So you can see that the minimum is on this blue one is much higher than the other minimums, and that's what's you want to take that out of the equation. And so what happens here is that this calculation then is this value 10,848.2 minus this guy. And when you do, you get that. You get 234.6. And then when you hit that minimum, 813.6, you get 0 right there. So now we have removed the 0. So you'll find there should be a 0 value in every one of these columns right here. Okay, every one of them when that minimum is hit. Okay, so now we've removed the minimum, and you can see now that they are all centered. They're all drawn right around 0. You can just barely see this, but there it is right there. Let's see if let me just move in a bit here, and you can see that it's very close to 0. Okay. So I'll move back out. And so what do we do next? Well, now we want to take care of these maximums not being the same. And so what I did now is I looked for the maximum value in each of these columns now that the 0 offset has been removed. And so I find a maximum here, 1686.4. And there it is right there, 1686.4. And so we are, so that's where we are on this one. Maybe I'll move this down just a bit more. Maybe I can make it a little bit easier to read. Okay, and so we've done that on each one of them. We've found the maximum value. And what do we do with that? Well, we're going to ratio this maximum to 1,000, so that now every maximum, no matter what it is in this group here, is going to end up as being 1,000 in the next panel over here. And you can see that that's exactly what happened. All of them are now done that way. And what is the calculation? Well, here, of course, here's the error again, but here is the calculation, and oh, I can't, okay, that won't, okay. Anyway, what I'm saying is if K3 is 0, then the output is 0, because there will be a 0, like right here, for instance. There will be a 0, and if you don't want to divide by 0, so if it's 0, it's going to be 0. So then K3 times 1,000 over K24. Well, K24 is this guy right here. It's the maximum. So we are taking this value, K3, which is right here, and we are saying, okay, we're going to multiply this by 1,000 over this guy. And we end up with something that says 139.1, and we go along, and again, the maximum number comes out to be 1,000. So you can see the 1,000 just coming up every time along here. And so now we've got these all normalized at 1,000. And notice and this is something that we really want to have. You can see that these intersections here between the various readings are, something on the order of halfway between the 0 and 1,000. That's what you want. You want to see those intersections to be maybe around halfway. If they're way up high, you got a problem. If they're way down low, you got another problem. You want them to be about halfway in between. Because what we're going to do next is we're going to take these normalized values and we're going to take each one of them and we're going to weight it. We are going to weight the numbers. So each one of these sensors now gets a weighting associated with it. And so there's one set that I call 8421. 8421, meaning that the two middle ones gets weighting of 1, and then the next two get a weighting of 2, and then the next two, the purple and the orange, they get a weighting of 4, and then the outermost ones get weightings of 8. So what I'm saying is that since they're as the car gets farther and farther away from the center of the path, the system gets much more excited about that fact. You're getting close to running off the track. You better do something. It's almost like guardrails. It's almost like guardrails. That's exactly what happens with guardrails. They get nothing, 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 and then bam, you hit it. And so it's not as sudden as guardrails, but it's along those lines. The farther away you get, the more excited it gets, and the excitement slopes up, and you can see that. Here is the plot for the 8421 weightings. And you can see, well, it's kind of flat as it passes through the origin, but the slope gets much steeper as you get farther and farther away in both directions. So note that we're in the first and third quadrant here, which is exactly what we want. If we're off to the one side, to the right, then we want to have nothing but we want to have positive values. If we're off to the left, we want to have negative values. That's how we know which way to turn. And the other weighting then is this one that I call 15, 14, 12, 8. And of course, it's all divided by 8. It's to get the scaling down to about the same as before, about the same. So, but here, it gets more excited the farther away you get, but the slope is not as extreme out here as the blue one. Where it really gets excited is when you get a little bit of an error right here at the beginning. If you're just off by a little bit, this thing really gets excited and is really trying to keep you right on the path. And so this is basically the opposite kind of concern. Here, yeah, you're both. The farther away you get, the bigger the value is of the sensor fusion output, which is appropriate the way it should be. But the blue one doesn't much care if you're off by a little bit or even a fair amount. It just doesn't care that much. The orange one, the 15, 14, 12, 8, that one really does care a lot, even with small errors. And so these are a couple of them. Now, this is one of the things that you'll be choosing. This will be one of your design decisions is, well, which one of these two you would be using for your weightings or some other weightings. A lot of students use different weightings from what I've suggested to them, and they do really well. One of the mentors, Winston Wang, had a second fastest car in his class by 1/10 of a second. and it was like the third fastest car in the entire class, and second fastest in his section, but I think it was the third fastest in the entire class. And he had, I forget what he had, but he had a, something very different from the two weightings that I'm suggesting here, these two weightings. But you can see what the calculation is. Here's the calculation. And so T3 gets multiplied by -8, and U3 gets multiplied by -4, and V3 gets multiplied by -2, and we just add them all up. We're just adding them up and dividing by 4. And so that's how we get from 8 numbers down to a single number. And that's the whole idea of sensor fusion. Now, this is the simplest kind of sensor fusion that you can come up with. There are all kinds of, autonomous vehicles today, well, semi-autonomous, level 2, level 3 autonomous vehicles. They are fusing either radar and cameras, radar and images, or LiDAR and images, and plus a whole bunch of other, they have several, sensors around the car. So to get what they really want is a 360-degree view of what is around the car. And so they've got all these different sensors, and they're all using them to come to a decision as to whether or not you should change a lane, or if you're getting too close to the edge of a lane, or this kind of thing, if you should speed up or slow down, all of those kinds of things. That all of these data sensors are fused into making a single decision, or I should say maybe a group of decisions, but each one of them has got basically a number that's associated with the desirability of making that decision. And so that's what sensor fusion is about. And this is an introduction to it. You're getting an introduction to sensor fusion very early in your engineering career at UCLA. But this is something that if this is the kind of thing that interests you, you're getting a very early look at it right here. So there's one other thing I want to point out. As you get, the farther and farther away, you're getting a larger and larger number until what happens? Until the final sensor starts, until all 8 sensors are outside the path. The path is outside all 8 sensors, and then bam, they drop off to very close to 0. And note that that's the same as the signal that you get when you are spot on. When the center of the car is over the center of the path, you get a 0 reading. And when the car is completely off the path, you get a 0 reading. If I'd have taken it further, you would have had a 0 reading over here as well. And so one of your jobs is going to be that your code is going to have to be able to distinguish between being spot on, which is right here, and being completely off the path. And how are you going to do that? So that's something to think about. I'll let you think about it for a while. And that's obviously the whole idea of this is to keep you from ever completely running off the path. But if you do, then you need to know that you've done it, and you need to come up with some kind of a path recovery routine. It's a different section of code. You just only go to that code if you have decided that you're completely off the path. Then what do you do? Okay, so basically this is the process that the sensor fusion goes through. Now what I want to do is to show you an ideal sensor fusion, a sensor fusion with ideal inputs, and that's what this third sheet is all about. You can see what they look like. These would be the kind of thing that we are actually looking for in our sensors, where there's some nice linear movement up to a maximum value that's the same on all of them. And the intersection points, as you can see, are about halfway. These are the kinds of, I just manufactured these numbers to make it happen. I went through the same process, subtracted the 0 out. The minimums were all 0, of course. The maximums were all 2,500. And then we go over here and calculate the the errors, and so everything is so ideal and everything else. So the payoff is right here. This is what the sensor fusion looks like for the if we had ideal sensor measurements in our calibration. Doesn't look a lot different. So here's what it looks like with the measurements that I actually took on my dining room table. And this is what it looks like if you just use ideal data. And again, here is the fall off to zero. That is, again, quite obvious. Looks very much the same as when you're spot on center of the car over the center of the path. So I just wanted to show you what it would look like in an ideal sense. And that if you're careful, you can come up with something that's not that far away from an ideal set of data. So I just wanted you to see that. So that's the end of the sensor fusion video. Thank you for watching.